This is Physics 241 Lab. Today's lab is Lab 8, and it's called Atwood's machine. All Atwood's machine refers to is a photo gate pulley with weights on both sides running around the pulley.
Okay, stop.
What we're trying...
Yeah, hold. Okay. Alrighty, keep on going.
What we're trying to demonstrate is F equals ma. And of course, if F equals ma, A equals F divided by m. And if we manipulate the things around, you'll find that A equals gravity times the differences in masses of Atwood's machine over the sum of the masses. And the masses we refer to are the masses down here where we're going to hang one mass M1 on the left-hand side of the pulley and another mass M2 on the right-hand side. And what this is going to demonstrate is when these two are not in equilibrium, the whole system is going to move, and we're going to measure that acceleration, and we're going to compare it to this calculated acceleration. We use, as I indicated, a photo gate pulley to do that. We're using Vernier software to generate the graphs, and from the graphs we can measure the acceleration of the weight system, and we're going to do it in two parts. In the first part, the two masses M1 plus M2 are going to equal 400 grams, and we're going to take a little bit off the one side then and add a little bit more to the other side. But in all cases, M1 plus M2 are going to still equal 400 grams. And we're going to measure the acceleration of the system. In our second part, we're going to have a constant differential of weight of 20 grams. M1 will always be 20 grams greater than M2. And we're going to, again, measure the acceleration of the system. And we're going to compare it to our calculated acceleration. Calculated based on this information. Now, before we start, as you can tell, when M1 equals M2, there's going to be a 0 here in the denominator, and the acceleration is going to be 0, which makes sense. If there's 200 grams on this side, 200 grams on this side, the pulley's not going to move. There's going to be no acceleration. When we talk about measuring the acceleration, again, we're going to generate a V over T graph. It's going to look something like this. We're going to use the linear fit function of our Vernier software to measure the slope of this V over T graph, and that's going to be the measured acceleration. Now, I alluded to the fact that in the first part, we're going to have a constant total mass of 400 grams. In our first scenario, again, we're going to have 200 grams on this side and 200 grams on this side. The pulley's not going to move. You're going to have 0 calculated acceleration and 0 measured acceleration, so there'll be no error. In all the other scenarios, we add 5 grams to the M1 side, and we take 5 grams away from the M2 side. But the total of the M's is still going to be 400 grams. If we use this scenario with our acceleration calculation, we'll come up with these accelerations. And in the same situation, if we measure it, we'll come up with these accelerations. And as you can see from there, they're very close. They're somewhere between a 4 and an 8% error. In part 2 of this experiment, we have a constant mass differential on the M's. M1, we start with 120 grams, M2, 100. We add 20 to each side in the next 5 steps. So in our last case, we had 200 grams on one side and 180 grams on the other. We run through the calculation based on our equation shown earlier, come up with these numbers. At the same time, we measure the acceleration from the VT graph, come up with these numbers, and again finding a very small error somewhere between 4 and 8%. Now, if you look in your package, you're going to see a lot of questions related to this this slab and a lot of the nuances of it. But in general, our conclusion is this, is that F equals MA. Our data here confirms that in measurement and in calculation, F equals MA based on the measurement of the acceleration equals gravity times M1 minus M2 divided by M1 plus M2.